Before we talk about the complexities, let's make sure that we know what an algorithm is. An algorithm is just a set of instructions to perform some operation. It could be a simple function, it could be a program that takes in some input, does some processing, and gives us the output. There are mainly two features of an algorithm that we are mostly interested in: the time it takes to run the algorithm and the space it takes in the memory. Algorithmic complexity is the measure of how much time it takes to run the algorithm, called time complexity, and how much space it takes in the memory, called space complexity. There are three different notations used to represent the algorithmic complexity: big O, big omega, and big theta. Big O refers to the behavior of the algorithm in the worst case. Big omega refers to the best case, and big theta refers to the average case and lies between the worst and the best cases. We are mostly interested in identifying the worst case behavior, because if we know how the algorithm behaves in the worst case, we know the quality of the algorithm. Alright, enough with the theory. Let's see how we can calculate the algorithmic complexity. To calculate the complexity of an algorithm, we just count the number of statements our program has to execute. Let's take an example of a function called askinfo, which is just printing a couple of strings to the console. If we count the number of statements in this function, it is 1, 2, 3, and 4. So we can say that the complexity of this algorithm is 4. This complexity is also called constant complexity because it doesn't depend on the number of inputs that the user gives. It is always going to be 4 statements that it has to run. Such complexity is called constant complexity, and we use 1 to represent this. So no matter how many inputs are given to this function, it is always going to be considered as 1. Let's take a different example where the complexity depends on the input given to the program. Let's say that we have a function called printItems that takes in the items, it goes through the items and prints them one by one to the console. And now if we count the number of statements that our program has to run, so we have the declaration, so statement count would be 1, and then for each iteration we perform the check to see if we have reached the upper limit of the items, so 1, then we get the item from the array, 2, then we print the item to the console, 3, and then we have the increment for I, so 4. So the statement count would be 1 plus 4n. So the complexity of this algorithm is going to be O of 1 plus O of 4n. In the cases like this, when we have multiple complexities for the algorithm, we only take the complexity that has the highest significance in the complexity. So in this case, if we look at the complexity, 4n has the highest significance. So we can drop O of 1 and take 4n. Now in the 4n also, n has the highest significance because it depends on the number of inputs or number of items given to the function. So we can drop 4 as well and take n only. So the complexity for this function would be O of n. Here is the list of common complexities that you might come across. We will now look at the examples of each to understand how to identify one and also see how an algorithm with the given complexity might grow. Alright, so first of all we have the linear complexity O of n. If you plot the graph for this, where we have the inputs on the x-axis and we have the time or space on the y-axis, the growth of a linear algorithm looks like this, which means that with the increase in the number of inputs, the time taken or space taken is going to grow linearly. So O of 1, for one input it's going to be 1, for 2 it's going to be 2, 3 is going to be 3, and so on. So O of n is equal to n. Here is the example of an algorithm with the linear complexity, where n is the number of items. So if we keep increasing the number of items, we're going to have one more item to iterate on. So there is a linear growth. Next we have quadratic complexity. In quadratic complexity, the time or space taken scales with each increase in the number of inputs. So what do we mean by that? If we draw the graph for quadratic complexity, the growth looks like this. So if we have one input, so O of 1 is going to be 1. But if we put 2, now we have 4. If we put 3, we have 9. 4 is 16 and n is n square. So you can see that with the increase in the number of inputs, the time or space taken grows rapidly. The algorithmic example for this would be loop within a loop. So if we have n as the number of items, here we have the outer loop which goes from 0 to n, and then for each iteration we have inner loop that goes through all the items again. Alright, so next we have constant complexity. In the constant complexity, no matter what the input size is, the time or space taken remains always the same. So if we have one input, O of 1 is 1. If we have 2 inputs, it is still 1. If we have n inputs, it is still going to be 1. The algorithmic example for this would be a simple access of item from an array. So no matter what is the size of the names array, the array access is going to be always taking the same time. Alright, so next we have the exponential complexity. So O of 2 raised to the power n. If you plot the graph for this, it is going to look like this. So with the increase in the number of inputs, there is exponential growth in the time or space. So for one input, it is going to be 1. For 2, it is going to be 4. For 3, it is going to be 8. And n is going to be 2 raised to the power n. The algorithmic example for this would be, for example, if you're iterating through all the possible combinations of items in an array. Another example would be Fibonacci series. So with the increase in n, it is going to grow exponentially. Next we have the logarithmic complexity. In the logarithmic complexity, you can increase the number of inputs exponentially, but the time or space taken is going to grow linearly. So this is the next preferred complexity after the constant complexity that we saw before. So if we have 10 inputs, O of 10 is going to be 1. If we have 100 inputs, it's going to be 2. For 1000, it is going to be 3. 10,000 is going to be 4. And n is going to be log n. Here is an example of an algorithm with logarithmic complexity. So as you can see here, with each next iteration, we increment I in such a way that we only have to look at half of the items in the array. Another famous example for this would be the binary search. So we have a sorted array and we have to look for some, let's say, number in this array. So we start with the item in the middle and we check if the item that we are looking for is smaller than this item, then we take the left half. If it is greater than the number, then we take the right half. So let's say that we have the item that we are looking for, it is smaller than this number. So we will drop the right half and only take the left half. And we will keep repeating till we find the item that we are looking for. Alright, so now to summarize, here is a list of complexities that we have just seen. If we plot them all in one graph, the complexity of O of n is going to look linear like this, n squared is going to look like this, the constant complexity O of 1 is going to look like this, exponential complexity is going to look like this, and here is how the logarithmic complexity is going to look like. If we compare all of these graphs and see with the increase in the number of inputs how the time and space usage grows, here is how we can sort all the complexities from the best to the worst. So constant complexity is the best. The next one you should aim for is the logarithmic complexity. After that we have the linear complexity and so on. And that is all for this one.